We're going to be looking at two problems from section 5.4. This is on exponential functions and models. And as I get my pointer option open here, I got to go felt tip and I need to change the color. My desk is cluttered up here. Ink color, let's go with just the blue, almost the same blue as here. Now, when we look at this, we want to find the exponential function that models the data in this table. Now, remember what we have to start with. We have to recall that for an exponential function, it's going to be of the form y is equal to a, where a is some non-zero constant, times b, where b is a number greater than 0 but not equal to 1, raised to the x power. Now this is the form for an exponential model. What we need to do then is we need to determine what the a is and what the b is. And so let's first of all look at the a. One of our data values over here is this over here, if I can get my pen to work correctly, is this 0, 2. If I plug that in here, if I put in the 2 for the y, and then we still have a times, we're going to have b raised to the 0 power. Now I chose this one in particular because of the 0 over here, because I know that anything raised to the 0 power is going to be 1. So this is equivalent to having 2 is equal to a times 1. In other words, we have our a value is 1. Excuse me, a value is 2. And so this yields one of the two vital pieces of information that I need. I have that the a has to equal 2. Now let's go from here, and if I continue from here, we can now have that our y is equal to 2 times some b raised to the x power. To get the b here, what we want to do is we want to look at the common ratio that we have in our y terms. The easiest thing that we can do is to take the ratio between a couple of integers here. So if I take 6 divided by 2, that's equal to 3. If I would take another pair, if I take 18 divided by 6, the answer is still 3. If I do a little more difficult computation, like such as this one here, if I have 2/3 divided by 2/9, remember that if you divide by a fraction, you invert and multiply. So this is the same thing as 2/3 times 9/2, and again we get an answer of 3. So our common ratio between our y terms is always equal to 3. Our textbook often talks about the percent change. Our percent change here would be 300%. That's the same thing as talking about a common ratio. And so what I'm going to tell you now is that because of this, the b value is going to be equal to the 3. Hence, we're going to get our final answer for the problem. We're going to have that our model is going to be y is equal to 2 times 3 raised to the x. Let's just double check this for, say, x equal to 4. If x is equal to 4, I lost my pointer here, I'm going to have that y is equal to 2 times 3 raised to the 4th power. So that's going to be 2 times 3 raised to the 4th power. 3 times 3 is 9, times 3 is 27, times 3 again is going to be 81. And so then 2 times 81 is going to be 162. And lo and behold, that's what we wanted to get. And so this verifies that our model is accurate. This then completes the first part of what we wanted to do. And so we have examined a set of data and come up with the exponential model for that data. If we continue to the next problem here, in this one here, problem number 9, it says compute the first difference and the percent change of the outputs to determine if the data in the table below should be modeled by a linear or an exponential function. Let's first of all look at the differences here. Again, notice that our x values here always are just the integers 1, 2, 3, 4, 5. So this is a simplistic or a simple type of set of data. Now if we look at the common difference here, on the first one, if I take 6 minus 2, I'm going to have an answer of 4. 14 minus 6 is going to be equal to 8. And if I take 34 minus 14, we have an answer of 20. If I take 81 minus 34, what's that going to be? Okay, 11 minus, let's do that on the side over here. 81 minus 34, see what I get here. 81 minus 34, 11 minus 4 is 7, borrowed 1, and so 7 minus 3, this is going to be equal to 47. And so what we're getting here is that our common difference here, or the first difference, is continually increasing. So this does not appear to be a linear model. Now, in like manner, we want to take the common ratio. And so on the first one, the first common ratio, let me put a line down here. My first common ratio is going to be 6 divided by 3, or first, they call it percent change. This was supposed to be a 2, and so my answer is 3, or 300%. On the next one, if I take 14 divided by 6, that's going to give us a decimal approximation. Let me use a calculator here a second. This is not on the screen, but you can do this on your own. And if I take 14 divided by 6, according to my calculator, I have 2.3 approximately. And so, again, if I can find my cursor, here we are. I have an answer of about 2.3 repeating, just barely on the screen. On the next one, if I have 34 divided by 14, what's that going to equal? Well, according to my calculator, 34 divided by 14 gives me an answer of about 2.4. And so that's an answer of 2.4, or 240%, if you want to think of it in terms of percents. And finally, the last one, the common, what we're calling the percent change here, we'll have 81 divided by 34. And again, on my calculator, 81 divided by 34, I came up with an answer of about 2.4 again. Okay? And so what we have here, if when we look at the percent change, we have values of 3, 2.3, 2.4, 2.4. These are approximately the same number, or approximately equal. Therefore, the answer for this problem is that it's not going to be best modeled by a linear function. It's going to be best modeled by an exponential function. And so our answer for this one is the exponential function. This then completes our exercise 1 and 9. And I need to come out of here, and thank you.